TON 618 is so massive it defies imagination, a black hole over 60 billion times the mass of our Sun. But how can something this enormous even exist, and what does it mean for our universe? Together we'll dive into the mystery of the largest black hole ever found. If you enjoyed this journey, please like, subscribe and share, and tell us in the comments, do you think there could be an even bigger black hole waiting to be discovered? Thank you for watching. Now, let's begin. The universe on its grandest scales is not a random scatter of galaxies, but a connected web of filaments, clusters and vast empty spaces. This cosmic web stretches across billions of light years, its strands composed of dark matter gas, and galaxies bound together by gravity. TON 618 sits within this immense structure, one point among countless others, yet extraordinary for the extreme mass of the black hole at its centre. To understand this object, one must first consider the setting in which it exists, the framework of cosmic matter distribution that gives rise to galaxies and quasars. The web is revealed through surveys that map the positions of galaxies across space. These surveys show long filaments where galaxies line up, crossing at dense knots called clusters, and leaving behind enormous voids where galaxies are scarce. The gravity of dark matter sculpts this arrangement, drawing ordinary matter to its invisible scaffolding. Gas flows along the filaments, cooling and condensing to form galaxies. It is within such a galaxy located along one of these threads that the quasar shines its light, travelling across a vast expanse to reach Earth. The position of the source within this framework is defined not just by its coordinates in the sky, but by its redshift, a measure of how much the universe has expanded since its light began the journey. Its distance places it billions of light years away, so that the light reaching present-day observers began its journey when the universe was far younger. On these scales, time and space are intertwined, and to view a quasar is also to look deep into the history of the cosmos. This perspective highlights the immensity of the setting. Galaxies such as this one are not isolated. They exist within environments shaped by large-scale flows of matter. Gas streams along filaments toward galaxies, feeding their growth and sustaining activity in their centers. Surrounding each galaxy, invisible halos of dark matter provide gravitational wells that anchor stars' dust and black holes. The galaxy hosting this luminous beacon is part of this greater pattern, its black hole powered by the continuous inflow of matter, guided by the geometry of the web. From this outer vantage, the quasar is a single luminous point, one among many catalogued by astronomers. Yet its brightness is not random. It signals extraordinary processes at its core. The object appears as a beacon in the depths of the cosmic web, a marker of intense gravitational activity. The web itself provides context for why quasars are observed at certain epochs more frequently than others. In the early universe, galaxies were more actively fed by cold streams of gas, enabling central black holes to grow rapidly. This quasar is seen during such a phase when the cosmic web still channels abundant material inward. Its existence testifies to the ability of large-scale structure to fuel extreme central engines. Observing this source from Earth requires instruments capable of detecting faint light stretched across time and distance. As the universe expands, the wavelengths of light emitted by distant quasars are shifted toward the red part of the spectrum. This redshift encodes the history of cosmic expansion and places each quasar within the evolving web of galaxies. For this object, the measured redshift corresponds to a time when the universe was only a fraction of its current age. Seen in this light, the quasar is not only a distant object, but a messenger from an earlier stage of cosmic history. Its role within the web extends beyond its own galaxy as quasars influence their surroundings on larger scales. the radiation and jets they emit can heat and expel gas, altering how nearby galaxies form stars. This luminous source with its immense power output would affect the intergalactic medium in its vicinity, creating regions of ionized gas detectable by careful surveys. This feedback loop between black holes and their environments ties the fate of galaxies to the structure of the web. From the outer perspective, the quasar is thus both a product of its setting and an agent shaping that setting. The cosmic web provides the matter that feeds it, while the black hole system in turn radiates energy back into the web. The balance of inflow and outflow is central to the history of galaxy formation. For astronomers, studying objects like this within their large-scale environment allows a clearer view of how structure evolves over time. Maps of galaxy distribution show that luminous quasars often lie in overdense regions, precursors to the massive clusters observed in the present universe. The host galaxy may be embedded in such a region, marking a node in the network of filaments. Its position gives clues about how the larger structures assembled from smaller ones, how black holes grew alongside galaxies, and how the web itself matured from early fluctuations. Light from the quasar has crossed billions of light-years, traversing regions of space that are mostly empty, yet punctuated by intervening matter. Along the way, it may pass through clusters of galaxies, clouds of gas or filaments rich in hydrogen. Each of these leaves subtle imprints on the spectrum of the quasar's light, allowing astronomers to reconstruct the intervening structure. This luminous beacon is thus not only an object of interest on its own, but also a backlight illuminating the web it inhabits. The study of this quasar contributes to mapping the unseen connections that tie galaxies together. At this grand scale, the black hole at the centre is hidden from direct view, but its presence is inferred from the extraordinary brightness of the quasar. It is this brightness powered by matter falling into the central black hole that allows the quasar to stand out against the darkness of space. Without such activity, the galaxy hosting the object might be invisible at this distance. The quasar acts as a natural lighthouse, its beam cutting across cosmic time to reveal both its own nature and the structure of the universe. In this way, the largest black hole known is first encountered not as a horizon or a shadow, but as part of the luminous web of galaxies. The cosmic context establishes the scale of the story, beginning with the entire universe before focusing inward toward the host galaxy. This quasar is situated within a framework governed by gravity fed by filaments of gas and shining across a background of countless other galaxies. To understand its extraordinary central mass, one must first acknowledge this vast outer environment, where the web itself sets the stage for the growth of galaxies and the black holes within them. The light that reaches modern instruments from this quasar began its journey when the universe was much younger. The concept of redshift provides a way to measure how far back in time these photons were released. As the universe expands, the wavelength of light travelling through space is stretched shifting toward the red end of the spectrum. The greater the redshift, the longer the light has travelled, and the earlier in cosmic history it was emitted. For Ton 618, the redshift value is high, placing the moment of emission billions of years in the past when the cosmos was only a fraction of its current age. By analysing this shift, astronomers reconstruct not only distance, but also the evolutionary stage of the universe at the time the quasar's radiation first escaped. This object is therefore a direct messenger from an epoch when galaxies were still forming at a rapid pace. The early universe was denser, more turbulent and rich in gas. Gravity pulled matter into the first halos of dark matter, creating sites where stars ignited and black holes began their growth. In this setting, quasars became visible as black holes at the centres of young galaxies drew in vast amounts of material. The energy released from this process illuminated their surroundings, producing beacons that could shine across billions of light years. The quasar under study represents one of the most extreme examples of this phenomenon, with brightness that allows it to stand out clearly against the faint background of distant galaxies. Measuring redshift involves careful examination of the quasar's spectrum, the spread of its light into component wavelengths. Specific patterns known as emission and absorption lines mark the presence of elements such as hydrogen, carbon, and oxygen. These lines shift toward longer wavelengths according to the degree of cosmic expansion. By comparing the observed positions of these features with their known laboratory values, astronomers calculate the redshift precisely. In the case of this luminous beacon, the spectral data confirm that its light has stretched significantly, meaning the universe has expanded many times over since the photons were first released. This measurement anchors the quasar in both time and space, providing a coordinate within the cosmic web. The age of the universe at that moment can be estimated by models of expansion. When the radiation departed, the cosmos had only begun to assemble the complex structures we now observe. Galaxies were smaller, and more irregular stars were forming at intense rates, and black holes were in the earlier stages of their extraordinary growth. Observing such an object is therefore equivalent to opening a window onto an era otherwise inaccessible. The quasar's very existence demonstrates that even in these formative epochs, black holes had already achieved masses of incredible scale. Redshift also determines how faint or bright an object appears to modern detectors. As distance increases, light spreads out and its intensity diminishes. Quasars that can still be observed across such enormous spans must have been emitting prodigious amounts of energy. The quasar in question ranks among the brightest known, a testament to the efficiency of its central engine. This brightness is the reason it can be studied at all, for most galaxies at this distance are far too dim to detect. Thus, high redshift quasars act as natural probes of the early universe, their intense light tracing back through time and illuminating conditions otherwise invisible. The analysis of redshifted light also allows astronomers to study the material lying between the quasar and Earth. Clouds of hydrogen gas along the line of sight imprint absorption features onto the spectrum, creating a record of the intergalactic medium at various points in history. By examining these imprints, researchers reconstruct how gas was distributed and how it evolved as the universe matured. This luminous source therefore doubles as a background light, revealing the state of cosmic matter on its long journey toward us. Its role is both to display its own properties and to illuminate the intervening structure. The precision of redshift measurement has improved with larger telescopes and more sensitive instruments. Observatories on Earth and in space can collect spectra with fine resolution distinguishing minute shifts that correspond to vast stretches of space and time. In the case of this quasar, such tools confirm its place among the most distant and luminous known. These determinations require careful calibration, since light passing through Earth's atmosphere and through interstellar dust can alter the observed signal. Sophisticated techniques correct for these effects, ensuring that the redshift reflects the true cosmic expansion. The outcome is a secure placement of the quasar at an epoch billions of years in the past. From the standpoint of cosmology, such measurements are crucial for testing models of how the universe evolves. The distribution of quasars across redshifts maps the growth of structure and the changing availability of gas for accretion. High redshift quasars are rare, but they offer the clearest view of conditions when the universe was young. The presence of this source so early in history suggests that black holes can grow extremely fast, raising questions about the processes that allowed such rapid accumulation of mass. These questions continue to drive research connecting observations of quasars to theories of galaxy and black hole formation. The early context also sets the stage for understanding the environment around the quasar itself. At the time its light was released, the cosmic web was channeling material into young galaxies at high rates. Streams of gas flowed along filaments feeding central black holes and igniting quasar activity. The luminous beacon under study is therefore both a product of its epoch and a participant in shaping it. The intense radiation from the quasar would have influenced its surroundings, heating gas and affecting subsequent star formation in its host galaxy. This interaction between quasar and environment is part of the larger story of cosmic evolution. In examining the redshift of this object, astronomers gain a dual perspective. They see both the immense black hole at its core and the universe in which it lived billions of years ago. The measurement is not just a number, but a bridge to the distant past, allowing present-day science to connect with the earliest chapters of structure formation. Each photon carries information from that epoch stretched, but not erased by the passage of time. Together they build a picture of a universe still in the process of becoming, with quasars as brilliant markers of its progress. The study of this quasar's redshift thus represents more than a simple measurement. It is an entry point into the early universe, a means of aligning observation with theory, and a way of grounding the immense scale of cosmic history in a single luminous source. The quasar does not exist in isolation, but resides within a galaxy that serves as its host. To picture this galaxy is to imagine an enormous collection of stars, gas and dust bound together by gravity, and centered on the massive black hole. Although the details of its appearance cannot be resolved directly from such a distance, the general properties of quasar-host galaxies can be inferred from observations of closer examples and from the signatures imprinted on the light that reaches Earth. The host is likely a large galaxy rich in gas, because only such a reservoir could sustain the extraordinary feeding required to power the central engine. The surrounding stars form the bulk of the luminous matter, while interstellar gas provides the fuel that flows inward. Dust clouds scattered through the disk and halo absorb and re-emit radiation, contributing to the overall brightness seen at multiple wavelengths. The environment around the galaxy extends into the larger neighborhood of intergalactic space. Other galaxies may lie nearby, drawn by the same gravitational filaments of the cosmic web. Their interactions through tidal forces and occasional mergers help drive gas toward the central regions. These encounters stir up the interstellar medium channeling material toward the nucleus where the black hole resides. Such processes are thought to be critical in triggering quasar activity, as galaxies in quiet isolation often cannot deliver gas rapidly enough to fuel such luminous outbursts. The host galaxy of this particular source may therefore be part of a dense environment, one where encounters are common and supply lines of matter remain open. Observations of quasar hosts at similar redshift reveal disturbed morphologies, streams of stars pulled outward, and irregular structures suggestive of collisions. These features signal the dynamism of young galaxies in the early universe. They're assembling their mass not gradually, but through violent events, each of which can funnel fresh gas toward the center. The quasar under study likely shares this heritage, its immense brightness, fueled by the chaos of galactic growth. The stars themselves, though far from the central black hole, contribute to the character of the host. Their light blends into the background of the quasar's spectrum, faint but detectable with careful subtraction. In this way, astronomers learn about the stellar populations, whether they are young and blue, indicating recent formation, or older and redder, suggesting a more mature galaxy. In the case of high redshift quasars, evidence often points to vigorous star formation, occurring simultaneously with black hole growth. This parallel activity shows that galaxies and their central engines evolve together, each influencing the other through the balance of gas consumption and feedback. Dust within the galaxy plays a complex role. It both obscures and reveals, blocking visible light but shining in the infrared. For observers on Earth, the presence of dust complicates the view, but also provides crucial information. The reprocessed radiation indicates where gas is dense, where stars are forming, and where the central black hole is hidden from direct sight. In some orientations, dust lanes may obscure the nucleus, while in others the line of sight offers a clear view of the quasar. This variability explains why some galaxies appear as brilliant quasars, and others with similar engines remain hidden. The galaxy hosting this luminous beacon is therefore not only a container, but also an active participant shaping the way the quasar is seen across the cosmos. Beyond the galaxy itself lies the larger neighborhood where groups and clusters of galaxies interact. The gravitational field of the host ties it to surrounding companions, and together they trace the pattern of the cosmic web. In such regions, gas is more readily available streaming in from intergalactic space. This inflow sustains both star formation and black hole accretion, ensuring that the galaxy remains active. The presence of the quasar signals that the balance has tipped toward extraordinary central activity, with vast amounts of gas reaching the innermost regions. This activity influences the galaxy in return. Radiation and winds from the quasar can drive gas outward, suppressing further star formation in some areas while compressing clouds in others. This feedback loop alters the future evolution of the host, demonstrating that the galaxy and its quasar are locked in mutual exchange. The view of the host galaxy at such distances is necessarily indirect, yet multiple lines of evidence converge to paint a consistent picture. It is a massive system heavily supplied with gas engaged in rapid star formation and undergoing interactions with neighbors. Its central black hole has reached a mass unmatched by any known, and the galaxy's structure reflects the intense processes that allowed such growth. The quasar is therefore both a beacon and a clue, pointing to the nature of galaxies in the early universe and the conditions that fostered their evolution. The spectrum of the light carries imprints of the galaxy's interstellar medium. Absorption lines from elements within the host provide fingerprints of gas composition, temperature, and velocity. These features help trace how material circulates within the galaxy from the outskirts inward. Emission lines, broad and narrow, arise from gas energized by the quasar's radiation, mapping the regions near the nucleus. Together, these observations sketch a portrait of a galaxy, alive with movement, its components intertwined with the activity of its central engine. In considering the host environment, one sees how the story of a quasar cannot be separated from the galaxy around it. The star's gas dust and neighboring galaxies all contribute to the conditions that make such an object possible. The black hole may dominate the energy output, but without the galaxy's supply and its interactions, the quasar would not exist. This relationship extends outward to the cosmic web itself, linking the fate of individual galaxies to the grand structure of the universe. The host galaxy of this quasar thus represents a crucial step inward from the larger scales. It is the vessel that delivers matter to the central black hole, the setting that shapes how the quasar shines, and the context that grounds the study of this extraordinary object. By situating the quasar within its galaxy, astronomers align the brilliant point of light with the broader fabric of cosmic evolution, ensuring that even the most extreme singularities are understood as part of the larger story of galaxies and the universe itself. The galaxy hosting the quasar is not an isolated island of stars and gas, but is connected to the surrounding cosmos through constant flows of matter. From the vast filaments of the cosmic web, intergalactic gas streams inward, pulled by gravity into the deep well of the galaxy's dark matter halo. These flows are known as intergalactic inflows, and they provide the essential fuel that drives the growth of both stars and the central black hole. In the early universe, such inflows are particularly strong as filaments remain dense with cold gas. This continuous supply allows galaxies to form stars at prodigious rates and simultaneously deliver material toward the inner regions where the black hole resides. The quasar understudy shines as it does only because these cosmic rivers of gas continue to feed it. The inflows move across enormous distances, traveling from the low-density voids into the denser nodes of the web. Along the way, the gas remains cool enough to collapse into the galaxy without being shock-heated to high temperatures. Once inside the halo, the gas follows filamentary streams, sometimes penetrating directly to the central regions. This process is more efficient in the early universe when the overall density is higher and cooling times are shorter. The result is a steady inflow that replenishes the galaxy's interstellar medium and ensures that the quasar has access to a nearly constant source of fuel. Observations of galaxies at high redshift support this picture, showing evidence of strong gas accretion and rapid star formation occurring side by side. Without these flows, the galaxy would quickly exhaust its internal supply, and the central black hole would starve. The evidence for intergalactic inflow comes from multiple directions. Spectroscopic studies reveal absorption lines in the light of background sources, tracing streams of hydrogen falling into galaxies. Computer simulations of large-scale structure predict similar behavior with cold filaments channeling material into halos. These simulations also show that massive black holes, such as the one powering this quasar, could not have grown so rapidly without continuous feeding from their environments. The combination of observation and theory gives confidence that the inflow is real and fundamental. The inflowing gas does not travel alone. It brings with it metals elements heavier than helium, produced in previous generations of stars and expelled into the intergalactic medium by supernovae. As the gas falls back into galaxies, these elements seed new star formation and alter the chemistry of the interstellar medium. In the case of a quasar host, enriched inflows also contribute to the diversity of emission lines observed in the spectrum. This recycling of matter across cosmic scales ties the fate of galaxies to their environments, and shows that no object exists in complete isolation. For the black hole system in question, the inflow means that vast amounts of gas are continually available to spiral inward and release energy as radiation. The inflows also play a role in shaping the structure of the host galaxy. As gas pours in, it can settle into rotating disks, fragment into star-forming clouds, or collide with existing material to trigger bursts of activity. These processes give the galaxy its evolving shape and character. For the central black hole, the inflow represents a pipeline extending across millions of light-years, channeling matter from the cosmic web itself into the depths of the accretion disk. This direct connection between the largest scales and the smallest illustrates the continuity of structure across the universe. Intergalactic inflows can vary in strength depending on environment. In dense regions of the web where filaments converge, galaxies receive stronger flows leading to more rapid growth. The quasar's presence suggests that its host galaxy occupies such a region, benefiting from a privileged position along active filaments. This location ensures not only abundant fuel, but also frequent interactions with neighboring galaxies, further stirring up gas and driving it inward. The interplay of inflow and interaction sustains the extraordinary luminosity of the quasar. Astronomers cannot observe the inflows directly at this distance, but can infer them from indirect signatures. the high rate of star formation, the presence of a luminous active nucleus, and the overall mass of the galaxy all indicate a constant supply of fresh gas. In spectra, narrow absorption lines from intervening gas clouds suggest that material is falling toward the galaxy along defined pathways. Together, these clues support the conclusion that intergalactic inflows are fundamental to the quasar's existence. The gas itself, while mostly hydrogen, contains traces of other elements that alter its cooling properties. These traces allow the gas to radiate energy more efficiently, falling deeper into the galaxy's potential well. As the gas reaches the inner regions, it mixes with material already present, forming a reservoir that feeds both stars and the central engine. This reservoir is dynamic, constantly replenished by inflows, and depleted by outflows driven by radiation and jets. The balance between these opposing processes determines how long the quasar can shine at its current brightness. In the case of this luminous source, the balance appears favorable to accretion, at least during the epoch when its light was released. Inflows also affect the circumgalactic medium, the vast halo of gas that surrounds the galaxy. As new material falls in, it interacts with existing gas, creating shocks, turbulence, and mixing. These processes produce observable features in absorption spectra, giving astronomers a way to trace the ongoing activity. The circumgalactic medium thus becomes both a record of past inflows and a mediator of current ones. For the quasar host, the halo is not a static boundary but a dynamic zone where intergalactic and galactic material meet. The importance of intergalactic inflow extends beyond a single quasar. It is a universal process shaping galaxies across time and space. Yet in the case of an object this extreme, the flows are particularly significant, for only such abundant feeding can sustain the growth of a black hole, reaching tens of billions of solar masses. The inflows connect the outermost structures of the universe to the innermost regions of the black hole, linking the cosmic web to the event horizon. This continuity across scales is one of the defining features of cosmic evolution. For observers, the challenge is to piece together these connections from faint signals stretched across billions of years. Each spectrum carries hints of the gas that fell inward. Each measurement of luminosity reflects the efficiency of accretion, and each comparison with theory refines our understanding of how such a massive system came to be. The quasar is thus not only a subject of interest in itself, but also a tracer of intergalactic processes that shape the universe as a whole. In contemplating intergalactic inflows, one sees how the story of this luminous beacon begins long before the gas reaches the galaxy. It starts in the tenuous filaments stretching across intergalactic space, flows inward through the circumgalactic medium, and finally gathers in the nucleus. Each stage builds upon the last, ensuring that the central black hole remains fed, and the quasar remains visible across cosmic time. The existence of this quasar is therefore inseparable from the flows that sustain it, making the study of intergalactic inflows a key part of understanding both the host galaxy and the largest black hole known. Surrounding every galaxy is an extended region of diffuse gas that forms a boundary between intergalactic space and the denser material within the galactic disk. This region is known as the circumgalactic medium. It stretches across hundreds of thousands of light years, far beyond the visible stars, and acts as both a reservoir and a filter for material flowing in and out of the galaxy. For the quasar's host, the circumgalactic medium plays a vital role in sustaining the black hole system and shaping the galaxy's evolution. It receives inflows from the cosmic web, catches outflows driven by the quasar's radiation, and mediates the exchange of matter between the inner regions and the vastness beyond. Without this zone, the balance of feeding and feedback could not be maintained. The circumgalactic medium is composed mainly of hydrogen, but also contains helium and trace amounts of heavier elements expelled by earlier generations of stars. It is diffuse with densities far lower than the interstellar medium inside the galaxy, yet it extends over such vast volumes that its total mass can be comparable to that of the stars themselves. This makes it a crucial component of galactic structure. For the host of the quasar, the circumgalactic medium provides the pathway by which intergalactic inflows deliver fresh gas to the galaxy. Streams of material from cosmic filaments enter this zone, slow down, and interact with the existing gas. Some of the inflowing matter cools rapidly and sinks into the galaxy, while other portions remain suspended, forming a dynamic halo that can fuel future activity. Observations of distant galaxies show absorption features in the spectra of background quasars, revealing the presence of this gas even when it's too diffuse to detect directly. In the case of a luminous source like the quasar under study, the circumgalactic medium also becomes energized by intense radiation from the center. This radiation ionizes the gas-stripping electrons from atoms and creating extended regions of glowing plasma. The resulting structures can be traced through emission lines mapping the size and distribution of the halo. In some cases, powerful outflows driven by the central engine push against the circumgalactic gas, creating shocks and stirring turbulence. These interactions enrich the halo with heavy elements and heat the medium to temperatures of millions of degrees. The result is a complex environment that reflects both the inflows that sustain the galaxy and the outflows that regulate its growth. For the quasar host, this balance is delicate. Too much inflow without regulation would overwhelm the central regions, leading to uncontrolled star formation and instability. Too much outflow would deprive the galaxy of fuel, cutting off both star formation and black hole accretion. The circumgalactic medium mediates these processes, allowing gas to circulate, cool, and re-enter the galaxy over long timescales. This cycle of inflow and outflow is central to the co-evolution of galaxies and their central black holes. The structure of the circumgalactic medium is not uniform. It contains clumps, filaments, and bubbles, each with distinct properties. Some clumps are dense enough to collapse and rain down onto the galaxy, while others remain diffuse and hot. Bubbles inflated by quasar-driven winds can expand for tens of thousands of light-years, compressing surrounding gas and altering its dynamics. In this way, the circumgalactic medium becomes a record of the galaxy's past activity. By studying it, astronomers infer the history of inflows and outflows, constructing a timeline of how the galaxy has grown and how the quasar has influenced its surroundings. Observations with large telescopes and space-based observatories provide data on the circumgalactic medium around distant quasars. The signatures include broad absorption lines from hydrogen and metals revealing gas moving at high velocities relative to the galaxy. These measurements indicate that the halo is constantly stirred with inflows and outflows, overlapping in complex patterns. The host of the quasar studied here must possess a circumgalactic medium of extraordinary extent, capable of supporting both the inflow of material needed to feed a black hole of immense mass and the outflow generated by its powerful radiation. Computer simulations of galaxy formation show that the circumgalactic medium is essential for understanding why galaxies grow as they do. Without it, models cannot reproduce observed properties such as star formation rates and black hole masses. In the simulations, the halo acts as a buffer, absorbing energy and redistributing matter. For quasars, the circumgalactic medium explains how galaxies can sustain activity for hundreds of millions of years without exhausting their supplies. The halo stores gas from inflows and gradually releases it, ensuring a steady supply over long timescales. For the quasar's host, this mechanism must have been particularly efficient given the extraordinary growth of its central black hole. The circumgalactic medium also links galaxies to the larger intergalactic environment. It is not a closed system, but part of the cosmic web. Gas flows in from filaments, circulates in the halo, and may eventually be expelled back into intergalactic space by quasar-driven winds. This exchange enriches the cosmic web with heavy elements, altering the chemistry of future generations of galaxies. The quasar under study is therefore not only consuming matter, but also contributing to the enrichment of the universe with the circumgalactic medium as the interface where these processes occur. For astronomers, studying the circumgalactic medium is challenging because of its faintness. Yet the brightest quasars provide a unique opportunity. Their light shines through the halo, carrying imprints of the gas along the line of sight. By analysing these imprints, researchers reconstruct the structure, composition and dynamics of the circumgalactic medium. In the case of a quasar of this scale, the results are particularly revealing, showing a halo that is both vast and turbulent. The circumgalactic medium thus emerges as a vital component of the story, bridging the gap between intergalactic inflows and the central black hole. It gathers matter from the cosmic web, shapes how gas enters the galaxy, and responds to the outflows generated by the quasar. Without it, the galaxy would not be able to regulate its growth, and the quasar would not sustain its luminosity. This halo of diffuse gas, invisible to the eye but detectable through its spectral fingerprints, is as essential to the existence of the quasar as the stars and dust within the galaxy itself. In tracing its properties, astronomers see how the processes of cosmic evolution are woven together, linking the largest scales of the universe to the smallest regions near the event horizon. The circumgalactic medium is therefore not a mere boundary, but an active dynamic zone that sustains the cycle of matter and energy. For the quasar host, it is the stage upon which inflows converge and outflows disperse, ensuring that the black hole system can continue to grow and shine across billions of years of cosmic history. Closer to the center of the host galaxy, within a region only a few light-years across, lies a zone of gas clouds moving at extreme speeds. This is known as the Broadline region. The clouds here are not evenly distributed, but are arranged in a roughly spherical or disk-like configuration surrounding the nucleus. They orbit under the immense gravitational influence of the central black hole, and respond to the intense radiation pouring outward from the accretion disk. Because of their high velocities, often thousands of kilometers per second, the spectral lines they produce appear broadened when observed from Earth, creating the distinctive features that give this region its name. These broad emission lines are one of the most direct pieces of evidence for the enormous gravitational power at the heart of quasars. The gas in the Broadline region is illuminated by the ultraviolet and X-ray radiation, emitted as matter spirals inward. Photons strike the atoms in the gas, exciting electrons to higher energy states. As the electrons return to lower states, they emit light at characteristic wavelengths. Because the gas is moving at such high speeds in random directions, the emission lines are smeared into wide profiles. The width of these lines reveals the velocities of the gas, and from these velocities astronomers estimate the mass of the central black hole. For the quasar under study, the extraordinary width of the lines indicates a mass far exceeding that of any known black hole in the local universe. The Broadline region is not static but dynamic, with clouds constantly moving, colliding and dissipating. Some models suggest the clouds are embedded in a wind rising from the accretion disk, while others propose they are fragments of larger structures broken apart by radiation pressure. Regardless of their exact origin, the effect they produce is unmistakable. Their emission dominates the optical and ultraviolet spectra of quasars, allowing them to be identified across vast distances. For astronomers, this region is both a diagnostic tool and a window into conditions near the central engine. The size of the Broadline region can be measured using a technique known as reverberation mapping. In this method, variations in the brightness of the central continuum source are compared to the delayed response in the emission lines. The time delay corresponds to the light travel time between the central source and the gas clouds, giving a direct measure of the region's scale. For luminous quasars, the Broadline region spans light months to light years, a remarkable size compared to the tiny scale of the black hole itself. These measurements confirm that the Broadline region lies at an intermediate distance, bridging the outer galaxy and the innermost accretion flow. The chemical composition of the Broadline region also provides insights into the history of the host galaxy. The presence of heavy elements such as carbon, nitrogen, and oxygen indicates that the gas has been enriched by previous generations of stars. This means that even at early epochs of cosmic history, galaxies had already undergone cycles of star formation and supernova explosions sufficient to seed the gas with metals. The quasar therefore records not only the dynamics of its immediate environment, but also the evolutionary stage of its host. The high density of the gas clouds, often millions of particles per cubic centimetre, ensures that they can radiate efficiently under the intense illumination. This efficiency makes them luminous beacons visible across billions of light years. The sheer brightness of the Broadline region contributes significantly to the quasar's overall spectrum, distinguishing it from other types of galaxies. Without this region, quasars would be far more difficult to identify at great distances. The Broadline region is also influenced by orientation. Depending on the angle from which the quasar is observed, some lines may appear stronger or weaker, and the structure of the profiles may vary. This orientation dependence is part of the broader unification picture of active galaxies, in which differences in appearance arise from viewing angles rather than intrinsic variations. For the quasar, being considered the observed Broadline suggests a relatively direct view of the central regions unobscured by dust. The stability of the Broadline region is remarkable, given the extreme forces at work. Radiation pressure from the central source tends to blow gas outward, while gravity pulls it inward. Magnetic fields may also play a role confining and shaping the motions of the clouds. The balance of these forces produces the turbulent yet long-lived structure observed. This equilibrium allows the Broadline region to persist over timescales long enough for astronomers to study, even as individual clouds may be short-lived. The presence of the Broadline region has broader implications for understanding quasar feedback. As gas clouds absorb and re-emit radiation, they contribute to heating the surrounding environment and may participate in outflows that extend to larger scales. In this way, the region links the inner accretion processes to the circumgalactic medium, serving as a conduit through which energy and matter are redistributed. This feedback influences star formation in the host galaxy and alters the evolution of its interstellar medium. In observing the Broadline region, astronomers also confront the limits of resolution. The region is far too small and distant to image directly, so all knowledge comes from spectra and variability studies. Yet these indirect methods yield powerful insights. The combination of line widths, time delays, and chemical signatures allows a comprehensive picture of the region's structure and role. For the quasar under study, these measurements confirm the presence of a black hole of staggering mass capable of binding gas at velocities unimaginable in ordinary galaxies. The Broadline region is therefore a crucial marker of quasar identity. It embodies the transition from galactic to nuclear scales, revealing the immediate response of gas to the gravitational and radiative power of the central engine. Its luminous signatures carry across the cosmos, enabling the discovery and study of quasars, even when the details of their host galaxies remain hidden. The story of the quasar cannot be told without the Broadline region, for it is here that the fingerprints of the central black hole are most clearly imprinted on the light. By focusing on this turbulent zone, astronomers gain a direct measure of the mass, energy and environment of the most extreme objects in the universe. The Broadline region thus serves as both evidence and explanation, bridging observation and theory, and anchoring the study of quasars in concrete measurements. For the luminous source being examined, the presence of broad lines of extraordinary width underscores the exceptional scale of the black hole at its core, situating it at the extreme end of cosmic possibilities and marking it as the largest known example of its kind. Encircling the central regions of the quasar lies a thick ring of dust and gas known as the dusty torus. This structure spans light years in diameter and forms a cocoon around the inner engine. It is composed of grains of silicates and carbon-based material mixed with molecular gas, dense enough to absorb and scatter visible light, but thin enough to allow radiation in the infrared to escape. The torus plays a defining role in how the quasar is seen from Earth, since orientation determines whether the central nucleus is directly visible or obscured. In the case of this luminous source, the viewing angle permits a clear sightline, but in other quasars the dusty torus hides the bright core, leaving only indirect signatures. This orientation effect explains much of the diversity observed among active galaxies and unifies them under a single framework. The dust within the torus is heated by the intense radiation from the accretion disk. As photons strike the grains, they raise their temperatures to hundreds of degrees Celsius, causing them to glow in the infrared. This re-emitted light forms a characteristic bump in the quasar's spectrum, allowing astronomers to infer the presence of the torus even when it cannot be imaged directly. The size of the torus is linked to the luminosity of the central engine. Brighter quasars push the inner edge of the torus farther out, since dust closer in would be evaporated by the intense heat. For the quasar under study, the radius of the torus must extend several light years, a scale vast compared to the black hole yet small in relation to the host galaxy. The torus is not a smooth structure, but a clumpy one with clouds of dust distributed unevenly. This clumpiness allows some radiation to leak through, creating partial views of the nucleus, even at orientations that might otherwise block the line of sight. It also produces variability in the observed brightness as individual clumps move across the view. The complexity of this structure underscores the dynamic environment surrounding the black hole. The dusty torus serves as both a shield and a gateway. It blocks radiation from escaping freely in certain directions, while funneling gas inward to the accretion disk. The gas and dust in the torus are gradually consumed, feeding the central black hole and sustaining the quasar's activity. At the same time, the torus regulates how energy and matter are exchanged between the nucleus and the larger galaxy. Radiation and winds from the inner regions heat the torus, stir turbulence, and sometimes drive outflows that expel material back into the host galaxy. Thus, the torus is not a passive bystander, but an active participant in the life of the quasar. Observations with infrared telescopes provide the most direct evidence for dusty tori. Space-based instruments capable of detecting mid-infrared wavelengths reveal the characteristic glow of heated dust, while interferometric techniques on large ground-based telescopes can resolve structures on parsec scales in nearby active galaxies. For distant quasars like the one under study, such detail is unattainable, but the infrared signatures are still strong enough to confirm the presence of a torus. The observed spectra show broad infrared emission consistent with large amounts of hot dust, confirming the model that places a torus around the central engine. The geometry of the torus is central to the unification of quasars and related objects such as Seyfert galaxies and radio galaxies. According to this framework, the same basic structure exists in all, but orientation determines the observed properties. When the line of sight peers through the opening of the torus, the bright nucleus is visible and the object is classified as a quasar. When the line of sight intersects the body of the torus, the nucleus is hidden and only scattered or reprocessed light is observed, leading to different classifications. This model explains why objects with similar central engines can appear so different, and it places the dusty torus at the heart of active galaxy research. The dusty torus also provides important information about the interplay between black holes and star formation. The dust grains themselves are products of stellar processes formed in the outer layers of dying stars and ejected into space. Their presence around the quasar indicates that the host galaxy has already experienced significant cycles of star formation and stellar death. In this way, the torus is a record of the galaxy's past as well as a participant in its present. It contains the remnants of earlier generations of stars now feeding the most extreme black hole known. The stability of the torus depends on the balance of gravity, radiation pressure, and turbulence. Gravitational forces pull the dust inward, while radiation from the accretion disk pushes outward. Turbulent motions within the gas clouds keep the structure puffed up, preventing it from collapsing into a thin disk. This balance allows the torus to maintain its thick donut-like shape over long timescales. Without such support, the dust would quickly settle or be blown away, altering the appearance of the quasar dramatically. The torus also plays a role in launching winds that carry material away from the nucleus. Radiation pressure on dust grains can accelerate them outward, dragging gas along. These dusty winds contribute to the outflows that shape the circumgalactic medium and regulate star formation in the host galaxy. In this way, the torus acts as both a source of inflow delivering gas to the accretion disk and a source of outflow expelling material into the galaxy. This dual role highlights its central place in the feedback processes that link black hole growth to galactic evolution. For astronomers, the dusty torus is a reminder that the most extreme objects in the universe are not defined solely by their central engines. They are embedded in structures that reflect the history and environment of their galaxies. The torus tells of stars that lived and died of dust that condensed and gathered, and of the balance of forces that shapes matter under extreme conditions. Its glow in the infrared carries across billions of light years, allowing observers to reconstruct its presence even when the details remain hidden. In the narrative of the quasar, the dusty torus is the next step inward, marking the boundary between the larger host environment and the innermost regions where gas spirals into the black hole. It is a zone of obscuration, reprocessing and mediation, ensuring that the energy of the central engine is both revealed and concealed depending on perspective. For the luminous source under study, the torus is vast, hot, and clumpy, an essential structure that completes the portrait of the active nucleus. Without it, the quasar's light would look very different, and our understanding of its workings would be incomplete. By examining the dusty torus, astronomers bridge the gap between the galaxy-scale inflows of gas and the final plunge of matter into the accretion disk, setting the stage for the extraordinary processes that occur even closer to the event horizon. Beyond the dusty torus, but still far inside the host galaxy, lies the accretion flow at larger radii, a zone where gas and dust begin to spiral inward under the pull of the central black hole. This region marks the transition from the turbulent, clumpy structures of the galaxy to the ordered yet violent dynamics of the inner disk. The inflowing material is not drawn in all at once, but gradually loses angular momentum, allowing it to move step by step closer to the center. At these larger radii, the flow is cooler and less luminous than the innermost regions, yet it plays a crucial role in supplying the fuel that ultimately powers the quasar's extraordinary brightness. The physics governing this flow is shaped by gravity, friction, and turbulence. As gas clouds fall inward, they collide with one another, converting kinetic energy into heat and redistributing angular momentum. This process causes some material to spiral closer, while other portions are flung outward. Over time, a net inward drift develops, and the gas begins to settle into a flattened structure that rotates around the black hole. This structure is the outer accretion disk, a vast whirlpool of matter stretching across light years in diameter. Although it cannot be imaged directly, its presence is inferred from the overall luminosity of the quasar and from models that match observed spectra. The outer accretion flow emits primarily in the optical and ultraviolet, with temperatures ranging from thousands to tens of thousands of degrees Celsius. Radiation from this zone accounts for much of the continuum light that defines the quasar's brightness. Embedded within the flow are magnetic fields, turbulence, and shocks, each shaping the behavior of the gas. In some areas, the gas is ionized and moves as plasma. In others, cooler molecular material survives radiating at infrared wavelengths. Together, these components create a dynamic environment where matter transitions from the relative calm of the galaxy to the extreme conditions near the black hole. Observations reveal that the outer accretion flow is not uniform. Variability in brightness on timescales of weeks to months suggests that instabilities ripple through the disk. These instabilities may arise from fluctuations in the rate of inflow, from turbulence driven by magnetic fields, or from the breakup of clouds entering the disk. As these instabilities propagate inward, they modulate the supply of gas to the central regions, causing the quasar's luminosity to vary over time. This variability is a hallmark of accretion processes and provides a way to probe regions too small to resolve with telescopes. The composition of the outer accretion flow also carries information about the history of the host galaxy. Spectral signatures indicate the presence of heavy elements mixed into the gas, confirming that the material has been enriched by generations of stars. This enrichment affects the cooling rate of the gas, making it more efficient at radiating energy, and thus more prone to collapse inward. Without such enrichment, the disk might behave differently, highlighting the connection between galactic evolution and black hole accretion. The dynamics of the outer accretion flow are influenced not only by gravity but also by magnetic fields. As charged particles move within the plasma, they generate magnetic forces that can both hinder and accelerate accretion. One key process is known as the magnetorotational instability, which stirs turbulence and allows angular momentum to be transferred outward. This mechanism ensures that gas continues to drift inward rather than remaining in stable orbits. Without it, the accretion process would stall and the quasar would fade. Thus, the interplay of magnetic fields and turbulence lies at the heart of how the quasar remains luminous. The outer regions of the accretion disk also act as a bridge between the Broadline region and the hotter inner disk. Gas clouds from the Broadline region may fragment and merge into the disk, adding to its mass. Radiation from the inner regions ionizes the outer layers, creating a layered structure with different temperatures and densities. This stratification influences the spectrum observed from Earth, producing a combination of continuum emission and line features that together define the quasar's signature. For the luminous source under study, the outer accretion flow must be immense, capable of sustaining a black hole of unprecedented mass. Models suggest that such a disk extends across thousands of astronomical units, dwarfing the scale of planetary systems yet minuscule compared to the galaxy as a whole. Within this disk, matter moves at high velocities, orbiting in periods of years to decades depending on distance from the center. Each orbit gradually drains angular momentum, allowing the gas to creep closer until it joins the hotter inner disk. Variability studies provide indirect evidence for the structure of this zone. By monitoring the light curve of the quasar, astronomers detect fluctuations that correspond to regions of the disk heating or cooling. These fluctuations travel inward, linking the outer and inner accretion processes. The patterns observed are consistent with models of large turbulent disks feeding central black holes. For an object of this scale, the outer accretion flow must operate at near maximum efficiency to deliver the mass required for growth. The interaction of inflow and radiation creates feedback effects that shape the disk. Strong radiation from the inner regions can heat the outer layers, driving winds that expel material back into the galaxy. These winds carry angular momentum outward and reduce the accretion rate, creating a self-regulating system. At the same time, pressure from radiation can compress parts of the disk, leading to localized bursts of accretion. This delicate balance ensures that the quasar does not exhaust its fuel too quickly, while still maintaining extraordinary luminosity. The study of outer accretion flows is inherently indirect. No telescope can resolve such fine structures at cosmological distances, but spectra and variability provide clues. By combining observations with numerical simulations, astronomers reconstruct the physics at play. These simulations show that outer disks are clumpy, turbulent, and threaded with magnetic fields, yet overall stable over millions of years. They provide the foundation upon which the inner accretion disk builds, channeling matter toward the event horizon. For astronomers, the importance of the outer accretion flow lies in its role as the supply chain of the quasar. It transforms diffuse interstellar gas into ordered orbits, regulates the rate at which matter reaches the center, and emits radiation that signals its presence across cosmic distances. Without this structure, the quasar could not sustain its brightness or feed its black hole. The outer accretion flow thus represents a critical step in the inward journey, narrowing the focus from the vast galaxy to the inner regions where gravity, radiation, and turbulence combine to create one of the most luminous phenomena in the universe. Deeper inward, the outer flow gives way to the inner accretion disk, the zone where matter approaches its highest temperatures and radiates its most intense light. This region lies only light days or even light hours from the event horizon, yet it produces the majority of the quasar's luminosity. Gas and dust here orbit at immense speeds, close to a significant fraction of the speed of light. Friction, turbulence, and magnetic stresses transform gravitational energy into heat-raising temperatures to hundreds of thousands of degrees Celsius. The result is radiation spanning the ultraviolet and X-ray ranges, combined with a bright optical continuum that defines the quasar's brilliance. The inner accretion disk is structured like a flattened whirlpool. Each ring of gas orbits faster than the one outside it, and the difference in speed generates shear. This shear, coupled with magnetic fields, produces turbulence that drags angular momentum outward. As angular momentum is shed, matter falls closer to the black hole, releasing gravitational energy in the process. This energy does not disappear into the black hole immediately, but is radiated outward, making the inner disk one of the most efficient energy-producing mechanisms in the universe. For the luminous source under study, the efficiency approaches the theoretical limits imposed by general relativity, allowing a small amount of matter to produce vast amounts of radiation. The spectrum of the inner accretion disk is a key diagnostic of its structure. Observed light curves show a smooth continuum shaped by the temperature gradient across the disk. Inner rings, hotter and denser, radiate in ultraviolet and X-rays, while cooler outer rings contribute optical light. Together, these regions create the multi-wavelength signature that astronomers use to identify quasars. For this particular object, the intensity of the emission confirms the presence of a black hole tens of billions of times the mass of the Sun, since only such a massive engine could sustain such power without immediately exhausting its fuel. The disk is not entirely uniform. Instabilities ripple through it, sometimes causing abrupt changes in brightness. These may be triggered by variations in the inflow rate from the outer disk, by turbulence generated by magnetic fields, or by localized heating events. In some models, portions of the disk can puff up into thicker regions, altering the pattern of radiation. These variations are visible as flickering when the quasar is monitored, over long periods offering a glimpse into processes occurring at scales far too small to resolve directly. The energy output of the inner disk is so great that it affects its own structure. Radiation pressure, the push exerted by light itself, competes with gravity and can drive matter outward in powerful winds. These winds emerge from the surface of the disk, carrying gas at thousands of kilometers per second. They contribute to the enrichment of the circumgalactic medium and play a role in regulating the accretion rate. In this way, the inner disk is not merely a passive supplier of light, but an active participant in shaping its environment. Another key feature of the inner accretion disk is the role of magnetic fields. As plasma orbits and twists, magnetic lines are wound into spirals. These fields channel energy and can launch jets perpendicular to the disk, extending far beyond the galaxy. While the jets themselves are discussed further inward, the base of these structures is anchored in the inner disk. Thus, the dynamics of magnetized plasma here connect directly to phenomena that influence intergalactic space on scales of millions of light-years. This study of inner accretion disks relies heavily on X-ray astronomy. Space-based observatories detect the high-energy photons that cannot penetrate Earth's atmosphere. These observations reveal features such as ion emission lines, broadened by relativistic effects. The shapes of these lines indicate how gravity bends light near the black hole and how fast the inner disk is rotating. In the case of extremely luminous quasars, the data suggest that the black hole may be spinning rapidly, further enhancing the efficiency of energy extraction from infalling matter. This connection between spin and radiation provides insight into how the black hole has grown over cosmic time. The structure of the disk also influences time delays observed between different wavelengths. Variations in X-rays often precede changes in ultraviolet and optical light, reflecting the sequence of heating across the disk. By measuring these delays, astronomers estimate the sizes of different regions and compare them to theoretical models. For the quasar under study, the inferred sizes are consistent with an accretion disk, scaled up to match the largest known black hole, confirming the validity of disk models across an extraordinary range of masses. The inner accretion disk is therefore a laboratory for testing physics under conditions unattainable elsewhere. General relativity, plasma dynamics, and radiation transfer all intersect here, producing phenomena that challenge both observation and theory. The disk demonstrates how gravity converts mass into energy with remarkable efficiency, outshining entire galaxies from a region only light days across. It also shows how local processes influence cosmic scales, as the energy released here drives winds and feeds jets that reach far into intergalactic space. For the luminous beacon being considered, the inner accretion disk is the heart of the quasar. Without it, the black hole would remain invisible, hidden behind an event horizon from which no light escapes. With it, the system becomes one of the brightest objects in the universe, visible across billions of years of cosmic history. The disk's light carries information about the black hole's mass spin and environment encoded in the spectrum and variability of its radiation. The study of such disks allows astronomers to measure black holes indirectly and to test models of how they evolve. This inner region also represents a step in the progression inward from the galaxy to the horizon. Each layer, cosmic web host galaxy, broadline region, dusty torus, and outer accretion flow funnels matter closer to the center. The inner accretion disk is where this journey culminates in the transformation of mass into light, the final stage before matter crosses the point of no return. For observers, the radiation from this disk is both a tool and a mystery, providing data yet hinting at processes still not fully understood. The extreme temperatures, rapid motions, and relativistic effects defy ordinary intuition, yet they are the natural outcome of gravity operating at its most intense. The inner accretion disk therefore stands as a bridge between the visible universe and the hidden realm inside the event horizon. It is the luminous skin of the black hole revealing what happens just before matter disappears forever. For the quasar that hosts the largest known black hole, this disk is vast, brilliant, and enduring a cosmic furnace that has burned for billions of years and will continue as long as gas flows inward from the galaxy around it. From the blazing inner accretion disk, attention turns to the role of magnetic fields and the processes by which energy is redirected into vast outflows. The plasma orbiting the black hole is highly ionized, meaning that it responds not only to gravity, but also to magnetic forces. As gas spirals inward, differential rotation winds magnetic field lines into tight coils. These twisted fields trap charged particles and channel them along paths perpendicular to the disk. At the same time, magnetic reconnection, where field lines break and reconnect, releases bursts of energy that accelerate particles outward. The combination of these effects creates the launching points of relativistic jets, the narrow beams of plasma that extend from the nucleus across intergalactic space. The importance of magnetic fields in quasars is underscored by their ability to transfer angular momentum. For matter to accrete, it must lose angular momentum, and magnetic turbulence within the disk provides a mechanism for this loss. The magnetorotational instability, a process unique to rotating plasma, stirs turbulence and allows angular momentum to flow outward while mass flows inward. This coupling between inflow and magnetic activity ensures that the accretion process continues steadily. Without it, the disk would stall and the quasar would dim. Instead, the luminous source persists, powered by a balance between gravitational infall and magnetic outflow. At the very inner edge of the disk, where plasma orbits closest to the black hole, magnetic fields intensify. They thread the horizon itself, forming structures that can tap into the rotational energy of the black hole if it is spinning. This process, described in theoretical models, provides a way to extract energy directly from the black hole's spin and channel it into jets. The result is a system where not only accretion, but also rotation contributes to powering the luminous output. For a black hole of extraordinary mass, such mechanisms may be essential to sustaining activity over billions of years. Observational evidence supports the presence of strong magnetic fields near quasar cores. Polarization measurements of emitted light reveal the imprint of aligned fields, while radio observations trace the synchrotron radiation, produced by charged particles spiraling around field lines. Variability in brightness often coincides with flaring events linked to magnetic reconnection, suggesting that these processes are active in real time. The consistency of these observations with theoretical predictions strengthens the case that magnetic fields are central to the behavior of quasars. The structure of the jet launching region is complex. Simulations show that field lines anchored in the disk and threading the black hole create a magnetosphere. Within this magnetosphere, plasma is accelerated outward to near-light speeds. The collimation of the jets or their remarkable narrowness arises because magnetic tension forces focus the plasma into beams rather than allowing it to spread. This focusing ensures that the jets can travel immense distances without dispersing, maintaining their coherence across thousands of light years. The efficiency of this process depends on both the strength of the magnetic field and the spin of the black hole. In systems with rapidly spinning black holes, jets are more powerful, suggesting a direct link between rotation and magnetic energy extraction. For the luminous beacon being considered, the jets must be among the most energetic in the universe, given the mass and brightness of the system. The connection between magnetic fields and jets also explains some of the feedback observed in host galaxies. Jets carry enormous amounts of energy into intergalactic space-heating gas, disrupting star formation and shaping the circumgalactic medium. These effects extend far beyond the central black hole, influencing the growth and evolution of the galaxy. Magnetic processes at the smallest scales therefore drive consequences at the largest, demonstrating the unity of cosmic physics across orders of magnitude in size. The study of magnetic fields near black holes remains challenging because of the impossibility of direct imaging. Instead, astronomers rely on indirect evidence, the polarization of light, the shape of spectra, the structure of radio jets, and the results of numerical simulations. Together, these lines of evidence form a coherent picture in which magnetic fields play the decisive role in connecting accretion to ejection. The quasar under study, with its exceptional properties, is a natural laboratory for testing these ideas, since its immense energy output makes magnetic effects more conspicuous. Magnetic fields also regulate the balance between radiation and matter in the accretion disk. In regions where gas is ionized, fields couple strongly to the plasma, creating turbulence that drives angular momentum outward. In cooler regions where neutral atoms dominate, the coupling weakens, leading to differences in behavior across the disk. This layered structure influences how efficiently matter spirals inward, and it determines the amount of energy available for radiation and jet launching. Understanding these processes requires not only observation, but also advanced simulations that model plasma physics under relativistic conditions. Such simulations reveal intricate patterns of turbulence reconnection and outflow, capturing the complexity of environments that cannot be recreated in laboratories. They also highlight the importance of feedback between magnetic and gravitational forces, showing how energy is partitioned between radiation and jets. For the largest known black hole, these processes must operate at extreme scales, amplifying effects that are subtle in smaller systems. The launching of jets is not the only outcome of magnetic activity. Winds less collimated than jets, but still powerful, also emerge from the disk. These winds carry away mass and energy, shaping the surrounding environment in different ways, whereas jets pierce directly through the galaxy. Into intergalactic space, winds spread more broadly, influencing the interstellar medium. Both phenomena originate in the same interplay of radiation, gravity, and magnetic forces, underscoring the centrality of the inner disk as the driver of galactic evolution. The role of magnetic fields in quasars exemplifies how unseen forces govern visible phenomena. Though invisible themselves, magnetic fields shape the trajectories of particles, the collimation of jets, and the variability of radiation. They are the threads that tie together the processes of accretion and ejection. For astronomers, the study of these fields offers not only explanations for observed behavior, but also insights into fundamental physics under conditions far beyond those achievable on Earth. In the case of the quasar understudy, magnetic fields represent the key to understanding how so much energy can be directed outward while matter continues to fall inward. The delicate balance of forces allows the system to remain stable despite the extremes of gravity and radiation. Without magnetic fields, the quasar would lack its defining jets, and its energy distribution would be entirely different. The central role of these fields ensures that the study of quasars remains not only a study of black holes, but also of plasma physics, turbulence, and the deep laws of nature. By focusing on the magnetic processes that launch jets, astronomers take another step inward, moving closer to the ultimate boundary of the black hole itself, while recognizing that the effects extend outward across cosmic distances. From the jet launching region near the black hole, the relativistic outflows extend outward, carrying plasma at speeds close to the speed of light. These jets are among the most dramatic and far-reaching features of quasars, visible across millions of light-years and influencing both the host galaxy and its surroundings. Each jet is a narrow beam of charged particles guided by magnetic fields, confined so tightly that they maintain coherence over enormous distances. They pierce through the interstellar medium, push against the circumgalactic gas, and eventually deposit energy into intergalactic space. For the luminous source under study, the jets are expected to be among the most powerful known, given the extraordinary mass of its central black hole and the luminosity of its accretion disk. The composition of relativistic jets includes electrons, positrons, and possibly heavier particles, all moving at relativistic speeds. As they spiral around magnetic field lines, these particles emit synchrotron radiation, a process that produces the radio emission by which jets are often detected. At higher energies, inverse Compton, scattering boosts photons to X-ray and gamma-ray energies, making the jets visible across the entire electromagnetic spectrum. Observations at different wavelengths therefore reveal different aspects of the jets. Radio maps show their large-scale structure. Optical observations trace shock regions, and X-rays highlight sites of extreme particle acceleration. Together, these data confirm the presence of jets extending thousands of parsecs from the central source. The narrowness of jets is remarkable. Despite travelling across such vast distances, they maintain widths of only a few light-years near their base. This collimation is achieved by magnetic fields which act like channels guiding the plasma. Instabilities do occur, causing jets to wobble, bend or flare, but overall their coherence is preserved. In some cases, jets can precess due to the rotation of the black hole or the gravitational influence of another massive object, leading to curved or helical structures. For the quasar in question, the jets likely extend far beyond the host galaxy, reaching into intergalactic space, where they inflate enormous lobes of radio emission. These lobes, tens of thousands of light-years across, mark the regions where jet material slows down and mixes with the surrounding medium. The energy deposited in these lobes is immense, heating intergalactic gas and preventing it from cooling to form stars. This feedback process regulates galaxy growth, showing how black holes exert influence far beyond their immediate surroundings. In this sense, the jets are not just spectacular phenomena, but also critical agents of cosmic evolution. The brightness of jets depends on the angle of observation. When a jet is aligned closely with the line of sight, relativistic beaming enhances its emission, producing a class of objects known as blazars. Although the quasar under study is not observed as a blazar, its jets still radiate strongly across the spectrum, detectable even at great distances. Their luminosity provides indirect evidence for the strength of the magnetic fields near the black hole, and for the efficiency of particle acceleration within the disk. Jets also exhibit knots and shocks along their length. These features arise when faster streams of plasma collide with slower material ahead of them, compressing and heating the gas. Such shocks accelerate particles to even higher energies, producing bright spots in radio-optical and X-ray images. The detection of these knots confirms that jets are not steady flows, but dynamic structures where energy is constantly redistributed. The variability of knots over time provides additional clues about the rate of ejection and the processes at work near the black hole. Relativistic jets can influence their host galaxies by carving out cavities in the interstellar medium. As they plow through the gas, they sweep material aside, creating channels that reduce the availability of fuel for star formation. At the same time, the shocks they produce can compress gas clouds, triggering bursts of star formation in some regions. This dual role, suppressing in some areas while stimulating in others, makes jets powerful regulators of galactic evolution. For a galaxy hosting the largest known black hole, the jets must have played a dominant role in shaping its structure. Beyond their galactic impact, jets serve as beacons for astronomers. They are visible at radio wavelengths across billions of light-years, making them among the easiest features to detect in distant quasars. By mapping their extent, astronomers trace the history of energy release from the nucleus and reconstruct how the central engine has evolved over time. For the luminous beacon considered here, the jets provide one of the few means of linking the unseen processes near the event horizon to the visible structures on intergalactic scales. The physics of jets also connects directly to the theory of relativity. As particles move at speeds close to light-time dilation, and relativistic beaming shape the observed emission. Spectra are shifted, brightness is enhanced, and variability is compressed. These effects allow astronomers to probe the relativistic regime in ways impossible in terrestrial laboratories. Each observation of a jet therefore tests fundamental physics as well as astrophysical models. The sheer length of jets is striking. Extending across kiloparsecs, they rival or exceed the size of the host galaxy itself. In radio images, they appear as long narrow filaments stretching away from a bright central point. In some systems, twin jets emerge in opposite directions, though often one is brighter due to relativistic effects. For the quasar under study, the jets are expected to display this bipolar structure with lobes at both ends marking the termination points. These lobes act as cosmic reservoirs of energy, glowing for millions of years after the jets that fed them have faded. Jets also interact with the circumgalactic and intergalactic medium in ways that enrich them with heavy elements. Material from the nucleus accelerated outward mixes with gas in the halo, spreading metals far beyond the galaxy. This enrichment alters the chemistry of the cosmic web and contributes to the evolution of future generations of galaxies. The jets of a powerful quasar thus become agents of cosmic recycling, carrying the products of stellar and nuclear processes into the vastness of intergalactic space. In studying jets, astronomers rely on instruments spanning the electromagnetic spectrum. Radio arrays map their structure in detail, optical telescopes trace shock features, X-ray satellites reveal high-energy processes, and gamma-ray detectors capture the most extreme emissions. Each wavelength contributes a piece of the puzzle, building a comprehensive picture of how jets form, propagate, and interact with their environment. The quasar being considered provides a particularly valuable case, since its jets are among the most luminous and far-reaching ever detected. The relativistic jets of quasars embody the connection between the smallest and largest scales in astrophysics. They originate in the twisting of magnetic fields just outside the event horizon, yet they extend across intergalactic space, influencing regions millions of light-years away. For the most massive black hole known, the jets are a natural consequence of the immense energy available, demonstrating how gravity, magnetism, and relativity combine to create some of the most striking features in the universe. Their presence ensures that the story of this quasar is not confined to its nucleus, but extends outward, linking the fate of the host galaxy to the broader evolution of cosmic structures. The radiation emitted by a quasar spans nearly the entire electromagnetic spectrum, from low-frequency radio waves to high-energy gamma rays. This broad output arises from a combination of physical processes occurring in different regions of the system. In the accretion disk, the primary mechanism is thermal emission. Gas heated to hundreds of thousands of degrees Celsius glows brightly, producing a smooth continuum of ultraviolet and optical light. This radiation dominates the visible spectrum of the quasar and accounts for much of its extraordinary brightness. Superimposed upon this continuum are emission lines created by surrounding gas, especially in the Broadline region where atoms are excited by ultraviolet photons and then release energy at characteristic wavelengths. These lines provide fingerprints of the elements present and the velocities of the gas. The dusty torus contributes infrared radiation, re-emitting the energy it absorbs from the central engine. This creates a distinct bump in the spectrum at mid-infrared wavelengths, which astronomers use to confirm the presence of dust even in the most distant quasars. Relativistic jets add further complexity. As charged particles spiral around magnetic field lines, they emit synchrotron radiation, producing the strong radio signals by which many quasars are first detected. The same particles can scatter lower energy photons to higher energies, generating X-rays and sometimes gamma rays through the inverse Compton process. This non-thermal radiation is highly variable and often polarized, distinguishing it from the thermal emission of the accretion disk. Together, these processes create a multi-wavelength portrait that allows astronomers to study quasars across the entire electromagnetic spectrum. Observing a quasar at multiple wavelengths provides a more complete understanding of its structure. Optical and ultraviolet data reveal the accretion disk and Broadline region. Infrared observations probe the dusty torus. Radio maps trace the jets and their extended lobes. X-ray and gamma-ray instruments detect the highest energy processes near the black hole. By combining these observations, astronomers can disentangle the contributions of each component and build a unified model of the quasar. For the luminous source under study, the spectrum reveals the immense energy budget required to power such radiation, confirming the presence of a black hole of staggering mass. Radiation processes also provide a means to estimate the rate at which matter falls into the black hole. The luminosity of the quasar is directly related to the accretion rate, with brighter quasars consuming more matter per unit time. By comparing the observed output to theoretical models of disk efficiency, astronomers infer how much gas is being accreted. For the largest known black hole, the required rates are extreme, suggesting that streams of gas from the cosmic web and the circumgalactic medium must continuously replenish the reservoir. Without such feeding, the observed luminosity could not be sustained. Spectral features also record the influence of relativistic effects. Near the black hole, strong gravity bends light and shifts emission lines. X-ray observations show broad iron lines distorted by gravitational redshift and Doppler broadening. The shapes of these lines reveal how fast the inner disk is rotating and how close matter orbits to the event horizon. For the quasar in question, such features imply conditions of extreme gravity consistent with a rapidly spinning black hole. These relativistic imprints turn the spectrum into a direct probe of spacetime itself. Variability across wavelengths adds further information. Quasars do not shine steadily, but fluctuate in brightness on timescales from hours to years. These fluctuations reflect changes in the accretion flow turbulence in the disk or shock waves in the jets. By monitoring variability, astronomers map the structure of different regions. For instance, when X-ray changes precede ultraviolet variations, it suggests that heating originates in the innermost disk and propagates outward. Long-term monitoring of the luminous beacon understudy shows patterns consistent with these processes, reinforcing models of quasar dynamics. Radiation also interacts with the surrounding environment. The intense output ionizes gas in the host galaxy, creating extended emission regions visible in narrow spectral lines. These regions trace the influence of the quasar on scales of thousands of light-years, showing how radiation escapes the nucleus and alters the interstellar medium. In some cases, radiation pressure drives outflows carrying gas away from the center at thousands of kilometers per second. These outflows regulate the supply of fuel and connect the radiation processes to the broader feedback loop between the black hole and its galaxy. The efficiency of radiation in quasars highlights a striking fact. Black hole accretion converts mass into energy more effectively than nuclear fusion in stars, whereas fusion releases less than 1% of mass, as energy accretion can release up to 10% or more. This extraordinary efficiency explains how quasars outshine entire galaxies despite their relatively small size. For the largest black hole known, the inner accretion disk radiates with such efficiency that its luminosity exceeds that of hundreds of billions of stars combined. This efficiency is central to understanding how black holes can influence cosmic evolution, despite occupying only a minuscule fraction of galactic volume. Multi-wavelength campaigns targeting quasars provide some of the most detailed views of these processes. Observatories on the ground and in space coordinate to monitor quasars simultaneously across the spectrum. Such campaigns reveal correlations between emissions at different energies, linking disk variability to jet activity or torus heating. In the case of the luminous source under study, these correlations help refine models of how energy flows through the system, from the infall of gas to the outflow of radiation. The study of quasar spectra has also advanced cosmology itself. Absorption features in the light of distant quasars trace the intergalactic medium, mapping the distribution of hydrogen and metals across cosmic history. These observations provide evidence for the large-scale structure of the universe and the evolution of matter over billions of years. The quasar is therefore not only a subject of interest, but also a tool for exploring the cosmos, its radiation carrying information far beyond its own environment. Radiation processes also test the limits of physics. The extreme energies, relativistic speeds, and gravitational fields involved create conditions where theories of plasma physics, relativity, and quantum mechanics intersect. Each spectral observation becomes a test of how well these theories hold under the most extreme circumstances known. For astronomers, the luminous output of the quasar is both a challenge and a gift, difficult to explain in all its complexity, yet rich with data that deepen our understanding of the universe. In considering the radiation of this object, one sees the culmination of processes operating across scales. Gas flows from the cosmic web, enters the galaxy, circulates through the circumgalactic medium, passes through the torus and spirals into the disk. Each stage releases energy, but it is in the inner regions that radiation becomes most intense. The result is a spectrum that spans all wavelengths, a cosmic beacon, visible across billions of light-years. For the most massive black hole known, this radiation is the defining signature, the reason it can be studied despite its distance. It transforms invisible gravity into observable light, turning a hidden singularity into one of the brightest objects in the universe. The light that travels from the quasar to Earth does not move in straight lines, as it would through empty space. but is bent and distorted by the immense gravitational field of the black hole. This effect, known as gravitational lensing, arises from general relativity, which describes how mass curves space-time and forces light to follow these curves. Near a black hole as massive as the one at the center of this system, the curvature of space-time is so extreme that photon paths are dramatically altered. Photons that pass close to the black hole may circle it several times before escaping, while others are pulled inward and lost forever beyond the event horizon. The result is a warping of the observed image and a modification of the spectrum as light from different regions of the accretion disk is bent toward the observer. The most direct consequence of this bending is the formation of a photon sphere, a region where light can orbit the black hole in unstable circular paths. For a non-rotating black hole, the photon sphere lies at 1.5 times the radius of the event horizon. In practice, photons rarely remain there for long, but the concept illustrates the degree of curvature at play. For a rotating black hole, the geometry is more complex, with photon orbits depending on spin and direction. In either case, gravitational lensing ensures that observers see radiation from parts of the accretion disk that would otherwise be hidden. Light from the far side of the disk is bent around the black hole, adding to the apparent brightness and altering the shape of the spectrum. This lensing produces what is sometimes described as the shadow of the black hole, a dark central region surrounded by a bright, distorted ring of light. Although this shadow cannot be resolved for the distant quasar in question, the same principles apply, and the observed spectrum bears the imprint of curved photon paths. Gravitational redshift also affects the light escaping from near the horizon. As photons climb out of the deep gravitational well, they lose energy shifting to longer wavelengths. This redshift combines with Doppler effects from the motion of the accretion disk, producing the broad asymmetric line profiles seen in X-ray spectra. By analyzing these profiles, astronomers measure how strongly gravity distorts light and estimate how close the emission originates to the event horizon. In the case of the most massive known black hole, these distortions confirm that matter orbits at relativistic speeds near the innermost stable paths. Gravitational lensing is not limited to the immediate vicinity of the black hole. On larger scales, the galaxy itself and surrounding structures bend light, creating additional distortions. In some quasars, this produces multiple images or arcs, when the light passes near other galaxies on its way to Earth. For this source, no such strong lensing has been detected, but the principle remains light traverses a universe filled with curved spacetime, and its journey encodes information about the matter it encounters. The bending of photon paths also enhances the brightness of quasars. By redirecting light that would otherwise travel elsewhere, gravitational lensing concentrates radiation toward observers. This effect, known as gravitational focusing, may help explain the extraordinary luminosity of the quasar, though the primary source remains the accretion of matter itself. Lensing thus contributes both to the visibility of the object and to the richness of the data available. The theoretical study of photon paths near black holes has advanced with numerical simulations that trace how light moves in curved space-time. These simulations produce images showing distorted disks, bright arcs, and warped rings of radiation. Although no telescope can resolve the structure of a quasar so distant, the agreement between simulated spectra and observed data confirms the accuracy of these models. They demonstrate how gravitational lensing shapes every photon that escapes from the vicinity of the horizon. For astronomers, photon trajectories are tools for probing the geometry of spacetime. The degree of lensing reveals the mass of the black hole, the extent of its spin, and the orientation of the disk. By matching observed spectra to theoretical predictions, researchers extract information about properties that cannot be measured directly. The quasar under study, with its extraordinary luminosity and distance, provides a stringent test of these models. Its photons have travelled for billions of years, carrying with them the imprint of gravitational bending near the horizon. Gravitational time delay also plays a role. Photons that circle the black hole before escaping take longer to reach distant observers than those that travel more directly. This delay creates subtle echoes in the variability of the quasar's light, with fluctuations arriving at slightly different times depending on their paths. Detecting such echoes requires precise monitoring, but in principle they offer another way to measure the structure of spacetime near the horizon. The interplay of lensing redshift and time delay turns the quasar into a natural laboratory for relativity. These effects demonstrate that light is not merely a messenger, but also a participant in the physics of black holes. Every photon reaching Earth from this system has been shaped by the curvature of spacetime, its path bent, its energy shifted, and its timing altered. Together, these modifications encode the presence and properties of the central black hole. On the larger scales, gravitational lensing can also amplify the quasar by passing through intervening structures. If a galaxy or cluster lies along the line of sight, it can act as a secondary lens, magnifying the quasar's brightness. While no strong lensing system has been identified for this source, the possibility illustrates how light from distant objects is influenced not only by their own gravity, but also by the cumulative mass of the universe. The photons we observe are shaped by every structure they encounter, making each spectrum a record of both local and cosmic conditions. In contemplating photon paths and gravitational lensing, one recognizes that the light from the quasar is not a simple beam, but a tapestry woven by gravity. It carries the imprint of curved space-time, the speed of orbiting gas, the depth of the gravitational well, and the long journey across the universe. For the most massive black hole known, these imprints are extreme, providing a rare glimpse into the limits of physical law. By studying how photons bend and shift, astronomers approach the edge of the event horizon, itself tracing the invisible boundary through the behavior of light. The bending of photon paths is therefore more than a curiosity. It is the key to unlocking the structure of black holes. The quasar under study, though distant, offers a stage where these effects are magnified, making visible the otherwise hidden warping of spacetime. Its photons, stretched and bent, tell a story of gravity at its strongest, of matter at its fastest, and of light at the edge of the possible. Moving still closer to the centre, one encounters the innermost stable orbits, the last paths where matter can circle the black hole without plunging inward. These orbits mark the boundary between regions where gas can radiate energy outward and regions where it is lost forever beyond the event horizon. The location of the innermost stable orbit depends on the spin of the black hole. For a non-rotating black hole, it lies at 3 times the radius of the event horizon, while for a maximally rotating one it can be much closer, even approaching the horizon itself. For a black hole of the scale present in this quasar, these distances correspond to billions of kilometers, yet relative to the size of the galaxy, they remain tiny, a microscopic zone in cosmic terms. The physics of the innermost stable orbits reveals how matter behaves under the strongest possible gravity. Gas that ventures this close moves at significant fractions of the speed of light, completing orbits in a matter of hours or days, depending on the black hole's mass and spin. The motion of this gas produces extreme Doppler shifts in the light it emits, stretching or compressing wavelengths depending on direction. When combined with gravitational redshift, the result is the distorted line profiles observed in X-ray spectra. These signatures provide some of the most direct evidence for the existence of innermost stable orbits, since they cannot be explained by processes at larger distances. Time dilation also becomes profound in this region. To an outside observer, clocks near the innermost stable orbit appear to tick more slowly. Events that take only minutes locally may correspond to hours or longer for distant observers. This effect is not noticeable in everyday life but becomes overwhelming near a black hole. For the luminous quasar under study, the immense gravitational field ensures that photons escaping from this region carry the imprint of slowed time. The variability of emission from the inner disk is stretched, and the observed frequencies shift, all consistent with the predictions of relativity. This time dilation also means that matter appears to hover as it approaches the horizon, fading rather than visibly crossing. In reality, the gas plunges inward once it passes the innermost stable orbit. But the external view is one of gradual disappearance, a reflection of the warping of spacetime itself. The innermost stable orbits are not only theoretical constructs, but practical tools for measuring black hole spin. By examining how close the disk extends before emission cuts off, astronomers estimate the rotation rate of the black hole. Faster spin allows orbits closer to the horizon, producing broader and more skewed spectral lines. In the case of this quasar, the features of the spectrum suggest a rapidly rotating black hole, consistent with models where spin contributes to the power of the jets. These measurements link observable light to the otherwise inaccessible properties of the hidden singularity. The region near the innermost orbits is also a site of violent turbulence. Magnetic fields twist, reconnect, and accelerate particles. Hotspots of plasma flare briefly as they orbit, producing variations in brightness. Monitoring these fluctuations allows astronomers to trace the motion of matter near the edge of stability. In some cases, periodic signals have been interpreted as the orbital frequency of hotspots near the innermost stable orbit. Such observations confirm the predictions of relativity and provide direct tests of gravity in its strongest form. The behavior of gas at these radii has implications for the efficiency of accretion. The closer matter can orbit before plunging, the more gravitational energy can be converted into radiation. For non-rotating black holes, the efficiency is about 6%, while for rapidly rotating ones it can exceed 40%. This difference explains why spin is such an important factor in quasar luminosity. For the largest black hole known, the extraordinary brightness suggests a combination of immense mass and rapid spin, allowing matter to radiate at maximum efficiency before crossing the point of no return. The innermost orbits also define the inner boundary of the accretion disk. Beyond this point, the disk structure dissolves and matter falls freely into the black hole. The transition is not abrupt but gradual, with the disk thinning and breaking into streams as it approaches the horizon. Radiation drops sharply, since in falling matter no longer has time to radiate before being swallowed. This decline in emission marks the edge of the visible universe, the boundary beyond which no information escapes. Observations of this cutoff provide further confirmation of theoretical models and anchor the understanding of black hole accretion. The concept of innermost stable orbits illustrates how relativity shapes not only the paths of light, but also the motion of matter. It shows that there are absolute limits to how close material can orbit, determined by the curvature of spacetime. These limits are not adjustable by conditions in the disk or the galaxy, but are fixed by the mass and spin of the black hole. In studying them, astronomers probe the geometry of spacetime itself. The time dilation near these orbits also highlights the difference between local and distant perspectives. For gas clouds orbiting the black hole, the passage of time feels normal. For distant observers, those same orbits appear stretched and slowed. This relativity of time is not an illusion but a fundamental property of spacetime, one confirmed by every observation of quasars. For the luminous beacon being examined, the photons arriving today carry the signature of slowed clocks, stretched by gravity during their escape. The study of innermost stable orbits bridges the gap between the luminous accretion disk and the hidden event horizon. It is here that matter shines its last before disappearing, where the laws of physics are pushed to their limits, and where relativity is tested most directly. For the largest black hole known, this region is vast by human standards, yet tiny compared to the cosmos, a ring of light circling a shadow that marks the edge of visibility. Its existence confirms that black holes are not mere abstractions but real objects, with measurable boundaries defined not by solid surfaces but by the geometry of spacetime itself. By observing the light from these final orbits, astronomers measure the shape of that geometry and test the predictions of relativity with remarkable precision. The innermost orbits thus stand as both the climax of the accretion process and the threshold of the unknown, the last stage where light escapes and the first step into the invisible realm within the event horizon. At the very threshold of the black hole lies the event horizon, the ultimate boundary beyond which nothing, not even light, can escape. This surface is not a physical barrier, but a one-way frontier in spacetime defined by the point at which the escape velocity equals the speed of light. For the quasar in question, the event horizon spans a diameter, measured in tens of billions of kilometers, making it larger than the entire orbit of Neptune around the Sun. Yet despite this unimaginable size, it remains invisible, a dark shadow against the brilliance of the accretion disk that surrounds it. The concept of the event horizon provides the framework for understanding what distinguishes a black hole from any other object in the universe. Within its boundary, all paths lead inward. Time and space themselves are so warped that no trajectory allows escape. For an external observer, matter approaching the horizon appears to slow and fade, never quite crossing, while in its own frame of reference it plunges inward in finite time. This difference in perspective is a direct consequence of general relativity, which describes the curvature of spacetime around massive objects. The event horizon thus represents not only a boundary of space, but also a boundary of perception. For the most massive black hole known, the scale of the horizon emphasizes the extremes at play. Its radius is proportional to mass, and with a mass tens of billions of times that of the Sun, the horizon extends across a region larger than most planetary systems. This size means that matter can orbit stably at great distances, but once it crosses the horizon it vanishes forever. No signal from inside can reach the outside universe, making the horizon the ultimate veil. Astronomers infer its presence not by direct observation, but by the absence of alternatives. No other phenomenon can explain the immense luminosity, the broadened spectral lines, and the relativistic effects observed. The event horizon is also linked to the notion of the black hole shadow. Although the horizon itself emits no light, gravitational lensing bends radiation around it, creating a dark central area surrounded by a distorted ring of emission from the accretion disk. This ring, predicted by theory and confirmed in nearby galaxies by very long baseline interferometry, cannot be imaged in a distant quasar, but its physics still applies. The light we receive from the quasar carries the signature of this curved spacetime encoded in spectra and variability. In this way, the event horizon, though hidden, leaves unmistakable evidence of its existence. Near the horizon, tidal forces shape the final stages of infall. As matter approaches the gradient in gravitational pull, stretches and compresses it, a process sometimes described as spaghettification. For a black hole of stellar mass, these tidal forces become destructive long before the horizon, tearing apart objects that come too close. For a supermassive black hole of the scale present here, the tidal gradient at the horizon is far gentler, allowing matter to cross intact before being destroyed deeper within. This distinction highlights how mass changes the nature of black holes, with the largest offering smoother passage across the horizon. Despite this, the ultimate fate of all matter that crosses remains sealed. It is cut off from the outside universe, adding to the mass of the black hole and contributing to its growth. The event horizon also defines the limits of measurement. Observers can study the effects of accretion radiation jets and gravitational lensing, but they cannot see inside. Physics beyond the horizon remains speculative, inaccessible to direct observation. For astronomers, this boundary is both a frustration and a profound reality check, reminding us that some aspects of the universe are beyond empirical reach. The quasar under study embodies this paradox. Its brightness illuminates the cosmos, yet at its core lies an absolute darkness. The scale of the event horizon also offers a measure of time. The period of orbit at its edge is linked to the black hole's mass, and the timescales of variability in the quasar's light curve reflect these orbital periods. By matching observed fluctuations to theoretical predictions, astronomers confirm the presence of the horizon and estimate the black hole's parameters. In this way, even the invisible becomes measurable, its properties inferred from the behavior of light and matter at its edge. The event horizon is therefore not an abstract concept, but a tangible part of astrophysical models shaping what is seen and what is not. In the broader context of cosmic evolution, the horizon represents the final step in the inward journey of matter that began in the cosmic web. Gas streamed along filaments entered the galaxy, passed through the circumgalactic medium, spiraled through the Torus and the accretion disk, and finally reached the innermost orbits. At the horizon, that journey ends. The matter disappears, and in exchange, the black hole grows. This process is repeated over billions of years, allowing the central object to achieve its extraordinary mass. The quasar's existence is thus inseparable from the horizon, for without it, the energy release of accretion would not be possible. The event horizon also symbolizes the limits of current knowledge. General relativity predicts its properties with precision, and observations confirm those predictions, yet what lies beyond remains uncertain. Theories of quantum gravity seek to describe the interior, but until observational evidence emerges, the horizon remains the final observable frontier. For astronomers, this boundary defines not only the edge of the black hole, but also the edge of science itself. The luminous source at the heart of this quasar demonstrates how far human understanding has advanced from mapping the cosmic web to measuring the structure of accretion disks, from tracing photon paths to estimating black hole spin. Yet at the core lies a region where knowledge ends, marked by the simple fact that no light escapes. The event horizon is both the conclusion of the narrative and the point at which further exploration becomes impossible. In contemplating it, one acknowledges the extremes of gravity and the boundaries of observation, recognizing that even the brightest beacon in the universe conceals a darkness that cannot be pierced. For the quasar hosting the largest black hole known, the event horizon is vast, silent, and final. The defining feature of a system that shapes galaxies and illuminates the cosmos, yet holds within it a region forever hidden from view.